So, number 1, here we go. We've got good old. And as soon as we're in orbit, then, okay, I can say gravity equals centripetal. Now, just because you're in orbit doesn't mean you say that automatically. You can go wait outside. Sure, go ahead. Instead, sometimes if it's work, you may use that later on. But for now, I said gravity equals centripetal. Big G, big M, little m over r squared equals m. And I'm going to use the one that has speed in it. We've seen this punchline before a couple of times. And r cancels, the mass cancels, and we end up with the orbital speed is big G, big M, little m over r. And when you crunch the numbers, you get... Come on, computer. Sorry, in the interests of time, I'm just going to rush through some of this stuff. Of course, in the interests of time, it would be much better if, in the interests of time, it actually opened the... Okay, there we go. Physics 11, Physics 12. Universal gravitation. Quiz 2, where are you? Quiz 2, version 1 answers. What do you get? Mark, what'd you get?
702 meters per second.
700?
702 meters per second.
702 meters per second? Yeah. That seems low. Is that right?
701.
Oh, okay. It is right? Oh, 7.0 times 10 to the second meters per second. Fair enough. 702 meters. Oh, you know why? Because that orbital radius isn't very high.
Yeah, it's pretty long.
Yeah. There you go. Okay. There's how I gave up part marks, but of course, if you got the right answer, 2 out of 2. B says, find the kinetic energy. Well, kinetic energy is a half mv squared. So I went a half times 2,500 times the velocity squared. Whatever answer you got for A, if you dropped it down to part B, if you dropped it down here and you squared it, I'll give you 2 out of 2 for part B, even if you got part A wrong. Hey, how else can I find the kinetic energy in orbit? Well, it's the same as the potential energy, but half of it and positive. You could have just gone that right there, and the advantage with that is you wouldn't be using velocity if you really wanted to be parallel. You wouldn't be using an answer that you found from part A, but we did say last class, it turns out that. Okay. Number 2, satellite orbits the Earth with an orbital period of that. What's the satellite's orbital radius? Okay. I'm still going to start out going gravity equals centripetal, big G, big M, little m over r squared equals m. But I'm going to use the one that has the period in it, 4 pi squared r over t squared. And in this case, the r does not cancel. So to get the r by itself, I'll get r cubed equals, mass cancels. Big G, big M, t squared divided by 4 pi squared. So I guess I can get rid of the cubed by cube rooting. When you do that, you'll get 1.8 times 10 to the 7th meters. Not very high. This is what happens when I make up numbers. What's the gravitational potential of this satellite relative to 0 at infinity? That means use the cosmic one, please. Potential energy is negative big G, big M, little m over r. Carefully crunching the numbers, you get negative 2.7 times 10 to the 10th joules. Half mark off if you missed the negative. Okay. Turn the page. Some of you are copying this down. I'll post this online later. You can always get it then. How much work? Now, the fact that we're lifted, we're not in orbit, so work is change in... Whoa. Change in potential plus change in kinetic. But since we're not in orbit, since we're just lifting it up there, that implies that it's just hanging there, little invisible angels or something are holding it up there. So the change in kinetic is 0. Change in potential is final minus initial. So it's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Minus minus is a plus. Oh, the other thing I'll have to do, Bree, is the fact that it's an altitude, I better add the Earth's radius to that. So I did. I said, okay, if I saw that gets you 1 mark. Negative, big G, mass of the Earth, mass of the satellite or object, radius of the Earth plus the altitude. Minus minus is a plus. Carefully, I crunched the numbers. I kept 4 or 5 sig figs, and then I added them together and said, oh, 2.71 times 10 to the 10th joules. I'd take 2.7 times 10 to the 10th joules. Again, if you know you're going to be using numbers, carry them to 4 or even 5 sig figs if you're going to be using those in further calculations. Final answer is 2 or 3 sig figs. Number 4. How much work? Well, now we're in orbit, so work is going to be change in potential plus change in kinetic. Okay, Mr. Dueck. I'm going to find the change in potential separately. I'm going to find the change in kinetic separately. Now, the change in kinetic is just going to be a half mv final squared, because we'll assume we're starting at rest. Change in potential is going to be the same approach as question number 3, except we're around the moon. Use the mass of the moon, use the radius of the moon. When I did that, for the change in potential energy, mass of the moon, 7.35 times 10 to the 25th. Radius of the moon, 1.74 times 10 to the 6th. They gave me a height, so I had to add that. Minus minus is a plus. I got, okay, the amount of work it takes just to get it up there is 2.41 times 10 to the 9th. Oh, and then it's kinetic energy. Now, this was nice, Jordan. They gave me the orbital speed. I would have no problem giving you the speed. I would have no problem not giving you the speed and making you calculate it just like you did in 1A by going gravity equals circular and getting V by itself. Anyways, 3.47 times 10 to the 9th. See a couple of fist bumps back there. This quiz probably represents about 60% of the written section of your test. Your test is a week from today. Okay, I'll be doing a tutorial Thursday after school. I'll send out tutorial videos tonight from previous years as well for those of you that can't make it Thursday. I know the basketball people can't. Okay. Can you give yourself a score, please, out of, count 'em, 15?